As we start to solve problems involving one-dimensional motion, I thought we just put up a little model here of what that situation might look like. So again, this could be a person walking on a sidewalk. It could be a runner on a straight track. It could be a car on a straight road. But either way you say it, we're talking about an object that can only move two directions, forwards and backwards. So here I've got a visual model. I've got like a little dot representing some object. It's going to start on this number line and move forward and backwards a little bit. And I'm going to start this timer up here. And we can watch the particle move back and forth for a little bit. So you can notice a couple of observations. It's not always moving to the right, and it's not always moving to the left. It's doing some of both. It appears that it's not always going the same speed. Sometimes it is speeding up, sometimes it's slowing down, etc. So we want to now take a look at how we could describe all of these actions with calculus. The key ingredient is to have an understanding that there is some sort of a function at work here. There is a function that is telling this particle where to be at any time. And we call that our position measuring function. So if I just stop this again here for just a moment, there is a function or an equation that tells this particle where to be. So if I'm going to scroll back to 0, and it looks like the equation or function is telling this particle to start at the number 1. And as I increase the time now just manually here, I can make the particle move directions, left and the right. But there's some kind of an equation telling this particle where to go. But we'd also like to be able to describe, as it's moving, how fast is it moving, and is that speed or velocity changing itself? And we're going to be able to answer all those questions. So let's start with today with a setup here where I'm going to give you the description that the particle is moving along the x-axis, just like my model was. We're going to study this particle for 10 seconds. And its position, like maybe its spot on a number line, is measured in feet. And the time is being measured in seconds. And the function that says where the particle is going to be this function here. The position function, s, is going to be the sine of t plus the cosine of 2t. And your time is going to be in seconds. The last video, we pointed out two other functions that come from this, and that's the velocity function, v, and the acceleration function, a. But even more than that, what was very important that we pointed out was how we find these. The function that says where the particle is measured in feet. And so the slope of that function is going to be measured in feet per second in this case. And so then we're talking about the derivative. Okay, as soon as we mention slope, we're talking about derivative. And so the function that measures the how fast information is going to be the derivative of the position function. So let's write that out using differentiation rules. The derivative of the sine of t is going to be the cosine of t. Now be careful on the second one. This is going to require the chain rule for the cosine of 2t, because the derivative, this is like cosine of u, the derivative would be negative sine of u multiplied by u prime. So there's going to be an extra 2 here because the derivative of 2t is 2. Negative 2 sine of 2t. And that gives us the velocity function. So if I want to know how fast it's moving, I could plug in a various time between 0 and 10 seconds, and it would tell me how fast it's moving. Also remember, if the value of this is positive, we know also the direction is to the right. It's moving to the right. And if the number this spits out is negative, I know that the motion is moving to the left. Now, acceleration tells us how fast the velocity is changing. Like maybe the particle is going from 1 foot per second to 3 feet per second. And therefore, it's accelerating. So that's the rate at which the velocity is changing. And so that's going to be its derivative. but it could also be thought of as the second derivative of the position function. So let's again work out the derivative of the velocity function. The derivative of cosine t would be negative sine t. And then again, using the chain rule, the derivative of sine of 2t is the cosine of 2t times 2. So this negative 2 is going to multiply by 2 cosine 2t and make negative 4 cosine 2t. All right, if you're going to follow along with us here on the video, I want you to take your graphing calculator and enter all of these equations into your calculator. So we're going to label the position function y1, we're going to call the velocity function y2, and we're going to call the acceleration function y3. I'm going to do that as well, so please pause the video and set your calculator up with those three functions. And here I'm showing my graphing calculator with those three functions already typed in. So the position function was sine of t plus cosine of 2t. Now, of course, we have to use x on the graphing calculator. For the velocity function, y2, we're going to type in cosine of x minus 2 sine of 2x. And then for the acceleration, the derivative of y2, so negative sine x minus 4 cosine 2x. This is also a good time just to show you that we don't have to graph all of these at the same time, even though we could. Right now, you see how two of my equal signs are bold or highlighted and one is not? What that means is if I hit the graph right now, it's only going to graph the blue and the red graph, not the black one. So watch what I do here. If I graph this, it's only graphing the blue and the red. If I want to graph all three, I'm going to go down to my third one, arrow over to the equal sign, and just hit enter there to turn it on. And by the way, that's the same way you turn it off, is just to enter on it again. But now all three are there, so it's going to graph the acceleration curve also. So now it's showing the position of the particle is the blue, the velocity graph is the red, and the acceleration is black. Now, in a minute, we're going to want to use only one of these. So in fact, I'm going to turn off the position function and I'm going to turn off the acceleration function for now. So we're going to go back and now only draw the velocity function. Okay, we'll explain why in just a minute. So let's go back to our problem and see what it is we have to, what things we're going to answer here. Part A was done. We found the velocity function here by finding the position's derivative, and we have found the acceleration by finding the velocity's derivative. Okay, now part B has three little parts here. Find the velocity and acceleration both at time 3. And then once we know both of those, we'll be able to answer these other questions. Is the particle moving to the forward or backward direction at this time? Also, is it speeding up or slowing down? Okay, we're going to do this entirely on the calculator. So for the first part, we simply want to find the velocity at 3 and then the acceleration at 3. So go back to your calculator. We're just going to do this with it, since we've already typed the equation that we need in there. Okay, I'm going to go to my TID4, and I'm going to quit away from the graph. So back to my home screen. And so the velocity was the y2 equation. So we're going to choose it by going alpha trace, and this lists all your equation names. We want the velocity, so we want y2 evaluated at 3. And it gives us negative 0.431, and we're going to go back and enter that. Negative 0.431. Let's do the same thing with acceleration by going to the calculator, this time choosing the third function, evaluated also at 3. It gives us negative 3.982. Now let's also label those if the position function measures everything in feet, and we know that the time in this problem is given in seconds, then the velocity is the slope of that graph, so it'll be measured in the unit of distance divided by the unit of time, feet per second. And the acceleration is the rate at which the feet per second is changing, so it technically is feet per second, but that can be abbreviated feet per second squared. Okay, so that's the way we're normally going to write the unit for acceleration. Distance per time squared, so feet per second squared. Now let's analyze those other two parts. Is the particle moving forward or backward at this time? Well, we can demonstrate that by noting, remember that the velocity's direction is indicated by the sign, positive or negative sign of the velocity value. So since this one is moving at negative 0.43 feet per second, the indication of the negative sign is that we're moving in the leftward direction right now, or the backward direction. So my conclusion is going to be written as, in a sentence, the particle is moving backward at the time t equals 3 because the velocity evaluated at 3 is negative. Okay, now I'm going to just make that a different color so we can read it better and it won't blend in with the other words there. Okay, so the particle is moving backwards at time 3 because the velocity at 3 is negative. So let's also talk about the second question. Is it speeding up or slowing down? It's a common notion, but it's actually a mistake to say that because the acceleration is negative, the velocity is decreasing, or therefore the particle is slowing down. It's possible to be speeding up in either direction. So let's use these two numbers together. This first measurement says at the 3-second mark, the particle is moving to the left at, let's just estimate it for a minute, at about negative a half feet per second. Okay, to round it to the nearest half, let's just say it's about negative 0.5 feet per second. But the acceleration is pretty close to -4. So what that is saying is, if it were to continue down this way for the next second, the next time I read the velocity, another second later, it's going to be going at about -4.5 feet per second, which tells me we're actually going faster because the velocity now is further away from being 0. 0 means it's not moving, and the further away from 0 it gets, the faster it's going. So because I was already moving to the left here with a negative velocity, and the acceleration is going to cause my velocity to become more negative, that technically means I'm gaining speed. I'm speeding up. Okay, so my correct explanation for this part is the particle is speeding up when t equals 3 because the acceleration at 3 and the velocity at 3 are both in the same direction. Let me explain that one more time here. It's because I was moving to the left at negative 0.4 feet per second. The acceleration is also negative, so it's telling me that soon after this, I'm going to be going about -4.5 feet per second. That is further away from being a velocity of 0 than it was, and that means I'm gaining speed. Okay. Before we go answer C, let's just fill in the next slide, which has a very kind of a note to self about what we just said there. The question about speeding up and slowing down. An object is moving in one direction and is speeding up if both the velocity and acceleration are in the same direction. Now that might mean both positive, it might mean both negative, but they have the same direction. As opposed to, we'll know the particle is slowing down if the velocity and acceleration are in opposite directions. I don't need to write the word directions, I guess, in opposite directions. So that's a big and that's an important thing there. For the question about speeding up or slowing down, you must use both the velocity and acceleration and note the positive and negative signs. Let's go back to part C now. Find the times and the positions when the particle is at rest. Now, I actually know there's many times during these first 10 seconds, so what we're going to do to save time is we're going to find just the first two. Times and positions when the particle is at rest. And this is going to be done entirely on the calculator. We just have to know which functions of those three to use. Do we need to use the position function, the velocity function, acceleration function? Let's first make a note, because some of you may not know what the phrase "at rest" means. You know, if you are resting, you're probably sitting still, not doing a whole lot, and that would mean you're not moving, and your velocity would be 0. So the synonym or context clue for this is if you see the word "at rest," it's another synonym for saying that the velocity, the value of the velocity, must equal 0. So in other words, to find these times, we must find the times when the velocity is equal to 0. Let's go to our graphing calculator and see the velocity function then and see how we're going to solve this. So I've got my velocity function y2 is the only one I'm graphing now. So I'm going to go ahead and graph. Let me just tell you that I've set my window to go on the x scale from 0 to 10. So I'm only seeing these 10 seconds that we're supposed to use. And I set my y scale, looks like about negative 1, 2, 3, 4, 5, negative 7 to 7. Okay, so the tick marks on both scales are counting by ones. All right. Now remember, we want to find when the velocity is equal to 0. And so since this is the velocity scale here, the y scale is the velocity scale right now, then I'm looking along the y equals 0 line, the x, which is the time axis, and noticing there's actually 1, 2, 3, 4, 5, 6. There's actually 7 times in the first 10 seconds where the velocity reading is 0. So we're only going to find the first two. The first one is somewhere between 0 and 1 second. The second time is somewhere between 1 and 2 seconds. So what we're going to do is we're going to find them with the calculator by having it find the zeros. And then we are going to find the corresponding location of the particle, the position at those times. Okay, but let's first get the calculator to find this first intercept right there. And so go to your second calc, and we're going to have the calculator find the 0. So we're going to choose number 2. Now, the calculator needs 3 inputs. It needs to give a left bound, a right bound, and a guess. So since I'm finding the one that's over here between 0 and 1, I'm going to use 0 as the left bound. I'm going to use 1 as the right bound, and I'm going to have a guess of about 0.5. And now the calculator found it to be 0.2526. I'm going to round that to 0.253, and I'm going to go ahead and write that down. And you know, I'm just going to subscript this time 1. Okay, and then I also want to find position. So I'm also going to use the calculator for that. Right now, this number is stored in the calculator in the memory slot called the answer slot. I now want to evaluate the position at that time. So I know the position is y1, and I'm going to go back to the home screen for a minute, call up y1, and I want to evaluate it at the time it just found. Now, I could type it in again, the first few digits, but the calculator has a way to recall the last answer. It's down here where it says answer in blue above the negative sign. If you just hit second answer there, it's going to use the previous answer it got, which was the 0.25 and whatever else seconds. And you can go read the answer right there without having to type that time in again. So I'm going to record the position as 1.125. And the label would be feet. This label would be seconds. Now we're going to go find time number 2 in the same way, and then position 2. Okay, I encourage you actually to pause the video here and just try this yourself. In a minute, I'll just pull up the 2 answers, and you can check for yourself. So I went ahead and found the other time and position, and so you can check your own. I found that it was also at rest, or the next time it was at rest was at 1.571 seconds. And then I plugged that into the position function. I actually got 0, which tells me that at that instant, not only was it sitting still, but it was actually sitting right on the middle of the number line at 0 feet. Well, I hope this helps, guys. I apologize, it's a little bit long today, but this was a really important topic that we'll be using throughout the rest of the course, is the topic of describing particle motion or objects in motion, the concept of position, velocity, and acceleration. Hope this helps with some of your assignment. Please let me know if you have any questions about any of the assigned problems. Next time we're together, we'll be working on the next topic of related rates. Hope to see you soon.